So before we've been talking about mathematical rules of probability. And let's review what the rules were together. We talked about the classical definition of probability. That's if we're trying to find the probability of a desired event. It's going to be equal to a ratio, where the ratio is the number of desired events divided by the number of total events. That was the first mathematical rule we talked about, and then we talked about the addition rule. And the addition rule, what kind of probability does that apply to? You guys remember?
Or?
Yeah, probability with events drawn by or. Okay. And if we have that, then we can split this up into separate probabilities drawn by addition. So this will end up being probability of A just by itself plus probability of B just by itself. But then technically there's this minus that has to be applied that has to do with the probability of any overlap between these individual events. So this will be the probability of both A and B. So this addition rule can actually expand into any number of events that are drawn by or. So for example, instead of just 2 events drawn by or, let's see if we can generalize if we had 3 events drawn by or. Then that's going to be the probability of each individual event added together. So that'll be the probability of just event A plus the probability of just event B plus the probability of just event C. But now it'll be minus the probability of any overlap between events. Oh, this should be A and B, not A minus B. And A and B is abbreviated as comma. So this will be probability of A comma B or A and B. Sorry. So the addition rule then says that you can add up the probabilities of each of the individual events, but remove any overlap. So remember when we first started talking about this, we said that we wanted to just add up all the probabilities once and made sure we added them all just once. So we have to remove the probability of any overlap between events. So you can have 2 events out of these 3 that overlap, for example, or all 3 could overlap. So if we list out all ways in which 2 events could overlap, it would just be, for example, this. And then these are all the ways that 2 events out of the 3 could overlap. And then all the ways that all 3 events could overlap is all 3 together. So this looks very complicated, but the point is that this just handles the probability of all the overlaps between multiple events. That's all you need to know is this is the probability of overlap. But the main part is that we're adding up the probabilities of separate events. Any questions so far? Okay, so in some special cases, we can ignore the overlap. So we can ignore the overlap when it's not possible to have probabilities with overlapping events. So for example, in this will be, under when we can ignore this, probability of overlap. So sometimes, we can ignore this. So let's talk about when it is that we can ignore this. So an example. Let's say that you're applying to schools, and last time when we talked about this, we made it simple, and we talked about how your rate of acceptance at each school was actually the same. But that's an oversimplification, because you know that some schools are easier or harder to get into than other schools. So let's say that you, the probability of getting accepted by school one let's say is 40%. So the probability is 0.4. The probability of getting accepted by school two is going to be, let's say, 20%. The probability of getting into school three, let's say that this is like a moonshot school, and let's say it's 5%. So let's say that you wanted to find the probability that you'll get into either school one or school two. So which mathematical rule do you think we use here?
Addition.
Yeah, the addition rule, because we have a probability with events drawn by blackboard. So that means that you can separate this out into probabilities that are drawn by addition, and then subtract out this probability of overlap, which we'll talk about. So this is the probability of getting accepted by just school one. Plus the probability of getting accepted by school two, and then minus the probability of any overlap, meaning that you get accepted by more than one school. Meaning that in this case, because there's only two schools, you get accepted into both school one and school two. So let's work out what this probability might be. What's the probability you get accepted by just school one?
40%.
Yeah, that'll be the 0.4 that's given directly. What's the probability you'll get accepted by school two? Yeah, 0.2. But now we need to subtract out the overlap. What's the probability that you'll get accepted by both? That means that school one has to accept you and school two has to accept you. So now we have a probability with events drawn by and. That actually is reviewing the third rule, the multiplication rule.
0.08.
And the multiplication rule says that the probability of events joined by and is the probability of the first times the next probability is actually a conditional probability. The probability of the second event given the first one occurred. So in this case, it would be, what's the probability that the first school accepts you times the probability the second school accepts you given that the first one accepted you. So what's the probability the first school accepted you?
0.40.
Yeah, 0.40. And now times the probability that the second school accepted you under the condition that the first school accepted you. So pretend that the second school already accepted you, and in that case, then now what's the probability the second school accepts you? Yeah, it turns out that if those events are independent of each other, which means it doesn't matter whether the first school accepted you or not. Let's say the admissions counselor don't talk to each other. So it doesn't matter whether the first school accepted you. Then the probability the second school accepts you is still 0.2. Then this ends up being 0.2 here. And this is when we would end up dealing with this probability of overlap. So usually you have to deal with this probability of overlap. You have to subtract this out. So then it would be 0.4 plus 0.2, which is 0.6, and then minus the 0.4 times 0.2, which is 0.08. So 0.6 minus 0.08. So this would end up being 0.52, it looks like. So that's a review. Any questions so far? No.
For any real life scenarios, would for like multiplication, if you were to use that, would they all be independent? Like every real life scenario, it would be independent, or?
Okay, great question. We're going to talk about more about that a little bit. Short answer is no, and short answer is in most cases in real life they're actually not independent. But sometimes we can simplify them to treat them as independent, even though technically they're not. And we'll talk a lot more about that. Okay, so so this is a review example to show that normally using the addition rule, we have the probability with events drawn by or, then you would have to be concerned with this subtraction element, with this subtracting the probability of any overlap. But in some cases, we can ignore this subtraction. So let's talk about when that might happen. Let's say that you have a coin, and let's say that no, maybe let's make it a little bit more practical than a coin. So let's say that you have this multiple choice test. And for the sake of the example, just to simplify the example, let's say you only have 2 questions on this multiple choice test. But let's say that there are 4 choices per question. And let's say that you wanted to know what's the probability that you'll get either 1 question right or 2 questions right. Let's say you guess on both questions. You want to know what's the probability you get either 1 correct or 2 correct. So here we have a probability with events run by or, so which rule can we use? Yeah, we use this addition rule here. And so again, the addition rule is we're gonna add up each individual probability and then subtract out any overlap. So this will be the probability of getting one correct plus the probability of getting two correct. And then subtract the probability that on the same test you get both one correct and two correct together on the same test. But what do you think this subtraction ends up being? What's the probability of getting both one correct and two correct at the same time on the same test?
0.
Yeah, it's 0. So this can't happen. You can't both on the same test get exactly one correct as well as get exactly two correct on the same test. So these two events we say are mutually exclusive. Or another word for that is disjoint. So these two events are mutually exclusive. So in real life, when you say that events are mutually exclusive, that means that they cannot happen together. So these are mutually exclusive or disjoint. Those mean the same thing. So if two events are mutually exclusive or disjoint, that means that the probability of them happening together is 0. So that means that in this case, you can ignore this probability of overlap. So in some special cases, in the addition rule, you can ignore this probability of overlap. You can ignore this subtraction here if the events can't occur together. So we have a special name for that, and the events are mutually exclusive or disjoint. Any questions? Yeah.
I'm sorry, why can't those two happen at the same time?
So they cannot happen at the same time, because this means that on the same test you get exactly one question correct if you were to guess, but also on the same test you get exactly two questions correct. So you can't have a score of one correct as well as two correct on the same test.
Okay.
So you would say exclude that from the problem then?
Yeah. So because this probability ends up being 0, you can ignore it because you're subtracting by 0. And so this is the main thing I wanted to show you, is that in some cases, using the addition rule, you can ignore that final probability. So it just ends up being that you're just adding up these two. But you can't always ignore it, only under some special cases. But in this case, you can. So that was the main thing I wanted to show you, but because we're talking about this problem anyway, let's go ahead and practice practice getting the answer. So let's go ahead and do the second probability first. It's a little bit easier. So how do you find the probability of getting two correct or both questions correct on this two-question test?
Use a multiplication rule?
Yeah, so if you wanted two questions correct, that means you must get the first question correct and the second question correct. There's no other possibilities to getting both questions correct. So you must get the first question correct and the second question correct. So probability with and is the multiplication rule. So then this would be the probability of getting the first question correct times the probability of getting the second question correct, given that you got the first question correct, or assuming you got the first question. So what would the first probability be of getting the first question correct?
0.25.
Yeah, 1/4, good, 0.25. And the second probability technically is conditional, which is saying that assuming you got the first question correct, that already happened, now you go to guess on the second question, what's the probability you'll get that second question correct?
1/4.
Turns out to also be 1/4. And it turns out that while we're talking about it, you notice that this second probability, even though it's a conditional probability, it ends up giving the same answer as this first probability, which was non-conditional. And so if this conditional probability is the same result as the non-conditional probability, we say the events of the conditional probability are independent of each other. So whether you get the second question correct is independent of whether you got the first question correct, because the probabilities here are the same. And we'll talk a lot more about independence in a little bit. But right now, we're focused on solving this problem in the addition rule. So, that's the probability of getting 2 questions correct. How do we find this probability of getting just 1 question correct out of the 2? It's a little bit tricky. So if we have only 1 question, the probability of getting that 1 question right will be 1/4. Now we have 2 questions, and we want to know what's the probability of getting any one of those questions right. Yeah.
Or it'd be 1/4 times 3/4.
Kind of. Okay, so let's talk more about that. So what we should do is, we should take this situation we're trying to find the probability for, and we should convert it into a logically equivalent statement that captures that situation in full. So 1 question correct out of 2 means that either you can get the first question correct, and you get the second question wrong, or you could get the first question wrong and get the second question correct. So only one of those situations could be true for you to get exactly 1 question correct, right? So again, 1 question correct means that you must get the first question correct and the second question wrong. I'll notate it this way. Or you can get the first question wrong and get the second question correct. And these are the only possibilities that could be true for you to get 1 question correct. So either one of these could occur. So just this one probability, you see, expands out to this situation. But now we have a probability with events joined by or, so which rule is this?
Addition.
This is the addition rule. So now, again, we're going to use the addition rule on this one part. So the addition rule is we're going to add up these individual probabilities and then maybe subtract out any probability of overlap. So again, we're going to add up these separate probabilities. And then what would the probability of overlap be? On the same test, can you get the first question correct and the second wrong, and also get the first question wrong and the second one correct? No, so in this case there is no probability of overlap because these events are disjoint. Okay, so you don't have to worry about this overlap. I'll just say probability of overlap. This ends up being 0, which you don't have to worry about. So now let's do these individual probabilities. What's the probability of getting the first question correct and the second question wrong? So notice probability of first question correct and the second one wrong. So probability with and is multiplication rule. So then we would multiply the probability of getting the first question correct, which is 1/4, and getting the second question wrong, which is 3/4. And then we would add that to probability of getting a question wrong, which is 3/4, multiplied by the probability of getting a question right, which is 1/4. So this result, if you were to simplify this, looks like 3/16 plus 3/16, and that looks like 6/16 if you were to simplify this. So the answer here is going to be the 6/16, and then plus this probability up here that we got getting both questions correct, which is 1/16 if you multiply 1/4 times 1/4. So 6/16 plus 1/16, that's going to be 7/16. So the answer here should be 7/16. So that'll end up being the final answer. So this is just a review problem which captures these mathematical rules that we've talked about. Using this addition rule, where you don't have to worry about the probability of overlap, because that ends up being 0. And then filling in these terms that are using both the addition rule and the multiplication rule. So this is a review. Any questions? Okay. So let's go ahead and, all right. So what's a third way that we could have solved the same question? Yeah.
The conditional probability, or doing the like inverse probability.
Yeah, excellent. So this, and now this is a review of the fourth rule that we talked about last time, and this is the rule of complements. So basically, this exact question, which we found by using the addition rule here, and you notice it was kind of complicated, because finding this probability of getting one correct actually expanded out into kind of many situations in which we had to account for. So it was kind of complicated, but that was one way to get the answer. But another way to get the answer was this rule of complements, which means that if you can think of the reverse situation, which is the complement, and you can easily find the probability, then you can use that and subtract from 1 to get the probability that you want. So the rule of complement says that the probability of an event is equal to 1 minus the probability of its complement. So in this situation, if you had a test with 2 questions and you wanted to find the probability of either getting 1 or 2 correct, then what does its complement represent? What's left out of this? Yeah.
Getting all of them wrong.
Yeah, getting 0 correct, or getting them all wrong, is the situation that is left out of this probability you're trying to solve for, so that represents the complement. So if we can easily find the probability of the complement, then all we have to do is subtract from 1, and we can get the same answer that we got here. So let's go ahead and try it. So we're trying to find the probability of getting either 1 correct or 2 correct. And we said that we can use the probability of the complement, which is getting 0 correct. So 1, and then subtract from 1. So 1 minus the probability of 0 correct. But another way of phrasing 0 correct is that means you get how many wrong? You get 2
1
wrong.
and 2.
Yeah, you get both of them wrong, good. So 0 correct, I'll just write it all out. So 0 correct. So sometimes it's hard to think of non-existence. So 0 just means that you don't have any correct. Sometimes it's easier to think of getting the actual existence part of it, which is getting 2 incorrect. So here we'll say this is the same thing as getting 2 wrong. So how do we find the probability of getting both of them wrong?
Multiplication rule.
Yeah, multiplication rule. So if we want both wrong, that means we have to get the first question wrong and the second question wrong, and that's multiplication rule. So what's the probability of getting the first question wrong?
4.
Yeah, 3/4. And then times the probability of getting the second wrong, given you got the first one wrong, but they're independent, so it's going to be the same probability. So this ends up being 1 minus 9 out of 16. And this ends up being 7 out of 16, which is exactly the same answer that we got using the addition. So you'll get the same answer, but out of these 4 rules, sometimes one rule might be faster and easier than the other rule, even though you'll get the same answer. So here, using the rule of complements, we happen to get the answer much quicker than using the addition. Questions? But this isn't always true. The rule of complements isn't always the fastest way. So depending on the situation, one rule will be faster than another rule. Any questions? Okay, so we saw that in the general case, this addition rule has the subtraction element. And sometimes this probability in the subtraction ends up being 0, so that sometimes you can ignore it. And you can ignore it when the events end up being disjoint or mutually exclusive. They can't occur together. That's in the addition rule. That's a special case of the addition rule. For the multiplication rule, you notice that in the general case, most of the time, there's this probability of an event given that the first one event occurred, so it's a conditional probability. So it turns out that sometimes you can ignore the conditional probability. If they're independent, then you can ignore this conditional probability. So here we'll say we can treat this as, we can use just the probability of just B without the condition if A and B are independent. So if these two events in the conditional probability are independent from each other, that means that if one happens, it doesn't change the likelihood of the second one happening, then we can ignore the second event in the conditional probability if they're actually independent of each other. So if these are independent, then we can ignore A and just use the probability of B. Okay, so this idea of independence is actually really important. So let's look at a concrete example to zoom in on independence some more. So again, we say that these two events in the conditional probability are independent if we can ignore the condition. So if we can ignore the condition and it equals just the probability of A, then these two events A and B are independent. So we'll say if A and B are independent, then this has to be true.
Even if I could be.
Oh, independent.
Okay, so that's right, B.
Oh, thanks. All right, so this is very abstract right now, but let me use a concrete example. Let's say that one event is that there are people at the beach. And let's say event B is that it's sunny outside. So the question is, are these two events independent of each other? So instead of talking it mathematically, let's talk about it conceptually. So independence means that if one happens, it doesn't change the likelihood of the other thing happening. So if it's sunny outside, does that change the likelihood that there are people at the beach?
Yes.
Yes, definitely, good. So because of that, we do not expect these events to be independent. These events are not independent of each other, they're dependent. So, but mathematically, we can reach the same result by seeing if this condition is met. So if this is met, then that means they're independent. But if they're not, that means they're dependent. So let's go ahead and try to look at these probabilities. So probability of A given B means that there's a probability of people at the beach given that it's sunny. Does that equal the probability that there are people at the beach, period? Okay, so let's examine the first probability. So just as an estimate, what do you think the probability that there are people at the beach is, given that it's sunny outside? So imagine only the days that it's sunny. What's the probability or the percentages that there will be people at the beach? Percentage of the time that there's people at the beach.
80%.
Yeah, so it might be sunny and cold maybe, so that maybe it'll be less likely in those days that there's somebody at the beach. But as a whole, usually if it's sunny, there's gonna be people at the beach. So maybe 80%. Good. But let's look at this other probability. What's the probability that there are people at the beach, period, regardless of the weather? So it could be sunny, it could be rainy, it could be snowing, it could be dark.
50.
Yeah, so 50, maybe even less, right? So let's say 50%, because that was suggested. So because these two numbers are different from each other, that means that these events are not independent of each other. So these two events in the conditional probability are not independent of each other because these probabilities, the conditional versus the non-conditional probabilities, end up being different from each other. Okay, so just like we expect, these events are not independent from each other, they're dependent. Any questions? But in the multiplication rule, if these two events are independent of each other, then you can ignore the condition. You can ignore this condition on A here and just use the probability of B. So this is a special case of when these events are independent, then you can ignore the condition. Any questions? Okay, so this is, again, is a review of all the mathematical rules that we talked about. And then some special cases in the addition rule if the events are disjoint, and a special case in the multiplication rule if the events are independent.